All right, so thank you for attending. My name is Ignacio Vigers. I'm a database consultant, and I'm working for projects at the University of Michigan, and I'm a back-end person. So I deal with a lot of databases or inner processing as opposed to GUIs. So today I will talk about the implementation of an actuarial research system used in SAS. SAS is very used in the insurance industry, although people complain that they reasonable to question whether to what extent will SAS to what extent is SAS suitable for implementing the systems that not only insurers need, but the topic of reserve is not exclusive to insurers, but also to other industries like banking, investment, healthcare, facility maintenance. So in this talk, we will focus on the insurance business, but many of the concepts apply to others as well. Well, I will start with by giving an introduction or background on the insurance business, but I will be making emphasis or moving towards the concepts of reserve and where they come into play. And after that background, we will see how this application, how this implementation works, and how it is appropriate for or how it is very useful for actuarial analysis or the analysis of loss, of contingencies and their development. Any questions? Please let me know at the same time. How do I do it? Oh, I see. So in a nutshell, when we wish to purchase insurance for a property or a car or a healthcare product, we as a customer pay a premium to the insurance company in exchange for the promise of financial help in the event of an unexpected loss or any contingency that was not foreseen. And from the side, from the perspective of the insurer, the company will collect the premium of all its customers, and that will become that we will call the earnings of the company. So now the task of the insurance company is to split those earnings in a way that it will bring profit to the company, to the stockholders, and it will and at the same time it will be able to meet its financial obligations to customers who may have experienced contingencies or accidents or somehow an unexpected loss. So for purposes of this talk, I've grouped the earnings in three categories. The first one is what I call operation expenses, and many of these are common to any business, not just insurance. All the companies have to pay taxes, payroll, maintenance, marketing of its products. In the case of non-insurance companies, they need to buy raw materials, which they use for producing the final output. So we are talking about tangible products in the case of factories or also service-intensive business. But in the case of insurers, there's no raw materials. Well, in the insurance company, we don't produce tangible products, and it is not a service-intensive business. So there's no reason for having this group of operation expenses be a high percentage of all the earnings. In other words, this group has to be a low percentage of the entire income. If it's high, then it means that either the company is operating inefficiently, or it's charging too low for the risk it is incurring. The second group is capital management, and this refers mostly to the profit for stockholders in the form of dividends, or how much it wants to, what facilities it wants to buy, or well, some of these assets may not be liquid, so they will be useless for responding to a claim from customers. And here I'm also including high-risk investments. If a financial product is too risky, then it is not reliable for responding a claim. Things may happen so that a customer experiences a huge loss, and if the insurer was relying on this product, and the price of this product went down, then there's nothing to cover that loss. And the third group is
For example, insurer, right? You have a small amount in a very, very risky venture. High yield is very risky. But because it's very risky, on a given day of the week, it could have crashed. And it's therefore effectively the same thing as an illiquid asset. I can't sell that today. I don't know when I can sell it. It might as well be real estate.
Yes. Yes, that's right. Exactly.
A bond that I can sell to another bond tomorrow.
Yes. Yeah, I mean, if it's, as long as you can convert it to cash relatively easy and without losing a substantial portion of the value, that will tell us if it's liquid and can use it for reserves, or simply it is not available for these operations. So in the third group, we have the resources that we can use for responding to obligations, and of course this is cash. This is the most immediate resource for responding to claims. Liquid assets, to what we were talking about. Low risk investments. They are included here because we can predict to some extent the value of this product. So this enables us to say, okay, we can use this product to cover likely losses in the future. But this involves less uncertainty, it is more certain than a high-risk investment in terms of time and/or value. And hedging instruments, unless they are high risk, like stock options, we can consider them as a reserve, as a component for reserves. Now, keep in mind that if speaking of stock options, we could count them as reinsurance if the underlying asset of the option is highly correlated to the risk exposure. The goal of the actuary is to estimate reserves so that we can say to the company what amount of the earnings needs to be allocated for eventual obligations to meet, and therefore the end result will be moving this the limit between these two sections. Stockholders want the capital section to be as bigger as possible, and we want to be on the safe side by not by making sure that we have enough resources in case needed. So with this, so the by defining this the limit between these two groups, we might get our company, our insurance company, one of these outcomes. If it might be profitable if we didn't assign too many resources for reserve. This means that we assigned we assigned a robust amount, and we could use the rest for investments or profitable operations. We satisfy both goals. The next level is solvent, which is less optimal than profitable, but at least we are in a safe position as an insurance company. Next level is risky. We might be nearing the area where we are making too risky investments that are too risky, and as such, we might not be able to cover the losses if they happen with an unexpected pattern, in a pattern that we didn't expect. When we incur into higher risk, most likely the company will have a regulatory body or an inspection to see how come we are getting into so much risk, and why we are not, or what guarantee we have to say that we can respond to the customers. And of course, insufficient resources might render the company insolvent or simply bankrupt, which is an extreme case of not being solvent. So this explains the need to project or somehow forecast the losses that the company will experience, well, via its customers. And the first question will be, is SAS a suitable instrument, or does it provide the right capabilities that we need for this analysis, as compared to SQL or many other commercial products about reserving, or even open source R language. As a database consultant, I work a lot with SQL, and along with this implementation, I have questions whether SQL always beats SAS or vice versa, whether SAS can do everything that SQL can, or whether it has its limitations. And I was surprised by some of the features found in SAS. One example is the online analytical processing. You might know how in SQL we have something called rollup to see the subtotals per categories, and I'm not sure if rollup is implemented in proc SQL of base SAS, but I found that it turns out that we don't need the rollup, because when we process a block of data in base SAS, we have well, the roll-up operation happens by default, so we don't even have to be concerned of whether proxy SQL contains that feature or not. So that's convenient. That saves us at least one operation. So in this more technical side of the presentation, we will see the structure of this implementation. We will see how it applies to how the actuary or the risk analyst can analyze or can project the losses, and we'll make then some comparisons or final remarks. In an insurance company, this is an example of claim details. For those who don't have a background in the insurance business, this O/S stands for outstanding, case outstanding, which means a loss is recognized by the insurer, but it is not paying that amount. So for the first claim, there was a loss reported, and insurer paid $400, and it has acknowledged that it needs to pay $200 later on, but the insurer is accepting this $600 amount for payment to the customer. And the same is for well, just like this first loss happened in 2005, this will entail further payments in the following years. So this is a data set that the insurer compiles with granularity, with a claim granularity. That is, at this point we haven't grouped any subtotals. And our first goal will be to group them and then classify and make conclusions by period and for how long they develop, for how long there are transactions related to these specific, to the claims specific to each year. So, starting from the raw data from our insurance company, we do the conversion the conversion so that the layout will be processed by our implementation. So in the example of the first claim, we reflect both accident and report dates. We have in another column the payments that were made right away, the payments that are promised to that customer. So here we see these variables or these columns holding the values of our original data. One of the most frequently used methods to project final losses is called chain ladder, and it consists of grouping data by period, say by accident year, or by the year that the policy was in force. And at the end, well, every year or every period, a company needs to report to the regulatory body how many resources it is keeping for possible losses. So that's why we need to at some point we need to identify the period of per valuation period, the amount that the company is supposed to keep, or that it forecasts that will be needed for claims. We also have to compute the claim development factors, which this is an important piece of projecting future losses based on what we already know, based on the losses that we are aware of. And later we will see the concept of tail factor, which is very it's essential, especially when we don't have enough data, or when losses may span several years, but we don't have data for that number of years. So this will be a generalization for scenarios of insufficient data, and this will serve the purpose of projecting the ultimate claims. That is, accounting for all the losses, regardless of whether they are currently reported or not, or what. This will be our forecast, our final forecast, so to speak. So I brought the application, the slides, but luckily we have SAS here, so we will be able to run the application here. No, here it is.
Yeah, good.
So we have some options, runtime parameters. An insurer may analyze the data based on the accident year, or like I said before, or policy year. That is the year when the policy was in force, or some other period that the inspector might require. Sometimes the insurance company wants to analyze the incremental cash flows or the incremental losses, but most often we analyze the cumulative losses to calculate or project the ultimate claims. Here we can aggregate both paid claims and case outstanding, or we can choose only one of these two components. And another variable is amount or count. Sometimes we care not so much about the amount, but the losses, the count of accidents. This relates to the frequency of an accident. So actuaries often want to make these analyses focusing on count as opposed to just the amount. So we will run with these variables grouped by accident year, and these are the results that the actuary wants to look at. Well, one feature I liked about SAS in this implementation is that while producing these results, the intermediary data structures can provide additional insight, and in case we need to restrict our analysis to a specific type of records. And this is done by default. This has to do with what I said about the roll-off that we don't need in SAS, because it's already implemented by default. It's already computed by default. We have we have the roll-up at all the levels we might ever need. So that was a nice feature. As a developer, I like that because I don't need to program more modules for a particular section or to get a particular result. Now, this H to H factor triangle reflects how they develop year by year. So this is the ratio. For example, this 1.6 comes from the ratio of this total, that is 2,420 divided by 1,500. This means that starting from this first loss, if we multiplied by 1.6, we will have a very close approximation of what we will expect for next year. And the same happens with the next periods. 1.12 refers to this ratio between the third and the second period, and similar for each other year. So for validation purposes, I wanted to bring the standard learning material for reserves. So we see the original data, and this is the same. This is what we got had we done the incremental version. Let's just run for now the incremental the variable with incremental results. So here we see cumulative paid claim. So we want cumulative and only the paid amount. So it's 600, almost the double next year. So 600, the double next year. So numbers match. So this is another feature I liked of SAS was that it didn't require extensive knowledge of multiple procs, or it doesn't require too many instructions. Basically, this implementation consists of proc summaries or sorts. So it was convenient. It doesn't require a steep learning curve to implement something that is already functional. So so here we see that this development, this H2H factor triangle, shows the proportion of how much our original loss will get to after some years. Now this data is, I think it was crafted for learning purposes, but in our case, it opens the door to further analyze the losses by time, or according to how they develop with time. The first year of losses, the behavior is essentially the same. We see the same ratio of 1.6. And similar behavior in both in every year. The second year has the same growth factor. So this starts pointing to a regular behavior of losses. This might not be the case in other lines of insurance. Some lines of insurance are more predictable than others. So it will not always be the case to see this regular progression of risk. Now, since each line of insurance will have different development or a different progression of losses, we need to decide if we will consider the losses as like they will span several years, or with just a few years we pretty much know what will be the total loss. And that brings us to the concept of short or long tail factor. Short or long tail. As an example of short tail, there's the car insurance. If there's an accident, it's easy to quantify the value that the insurer will have to pay to the car owner, and it cannot vary that much. But for other lines, like the asbestos liability, this can span several years, often 20 years or 30 years. So that one will be an example of long tail factor. And we don't have data for, we usually don't have enough data for long tail factors. So we need to make a projection of how it will develop when we don't have many years of loss numbers. So knowledge of the business will dictate or influence if we should consider this as long or short tail. The amount of data available, as I just explained, and the progression of claim development factors. If we go back to this H to H factor triangle, we see how from second to the third period, the factor goes down substantially goes down. But from the third to fourth year, it still goes down, but not as much as previously. So this might indicate long tail case where next factor might be 1.9. I'm sorry, 1.09, which will mean that the insurance company will have to keep paying for several years. Or if it's a short tail scenario, then we might likely have this as the last payment, and the loss will not go beyond the fourth year. Now, in this case, we have a small amount of data, so we cannot, we don't know if we are on short or long tail. So there are several approaches to define if it's long tail. There are multiple approaches. The most common is the curve fitting, but again, we have so little amount of data. We don't have enough data to fit a curve. So for this example, I made a quick derivation of ratios. As you can see, the H to H triangle divides. Well, it wants to compute the long tail based on this ratio of this number 1.12 and 1.11. So 1.12 and divided by 1.11 this gives ratio of 1.01. And we want to see how many periods, assuming this this progression factor, we want to estimate how many periods it will take for us to reach the final, the last development of costs or losses. So from this particular example, we get that after 8 periods, we might get, assuming with this assumption, after 8 periods, we might get the final development. But keep in mind that we only have 4 periods of data, so this is clearly insufficient. The data we have is not enough to make a conclusive projection. So our resource is to define our tail factor as the claim development factor divided by this other ratio that we have, applied by n number of applied for n periods. In this case, 8. So we got we got 2.08, which is very far from 1. 1 involves more certain knowledge of loss development. This tail factor involves more leverage. So we will run the application with same parameters, but we will modify the tail factor. Now, before we do so, let's see the result of assuming the tail factor is 1. For example, in the case of 2005, we have $1,800 for losses. Now we will run the program, but now with a bigger tail factor, the one that we got. So we will see from 1,800 for 2005, it now went to the double, almost 4,000. So this shows the leverage of using a tail factor, and therefore the leverage involved in long tail or long run scenarios. So the actuary goes back and forth, trying assumptions of these triangles, estimating the tail factor based on specific assumptions like we did here. And at the end, the actuary obtains numbers or global results, and these are recommended to the company to keep as available in case of losses. Or the government or the regulatory body will inspect that the company has consistent assumptions, and that the company is keeping enough resources. In other words, it's making reasonable assumptions and sticking to them. So, like I said, we're nearing the closing point. Like I said, Baked SAS was enough. It gave enough capabilities or enough programming resources to implement all this functionality without the need of proc SQL or external languages. we saw how from the original data, the claims data that the adjuster gave us, we were able to produce the final or the ultimate claims or their projection. Now, I found this comparison between proc SQL and base SAS on performance, saying that for low volumes of data, proc SQL is better, and for bigger data, base SAS is better. It's hard to tell the reason why it is the case, since we don't know the engine or the inner details of the SAS engine. But it was interesting. As an example, in AS400, it's the opposite. SQL turns out to be faster than the RPG or other languages. Now, there was another study which compared the performance of SAS and open source R, also the commercial version of R, which is called Revolutionary Analytics. And that study concluded that SAS completed the work, but it took longer than other technologies, namely longer than Revolutionary Analytics. But it completed the work as opposed to other options. For example, open source R did not complete the job. It had several days running the process, and we couldn't see the results. And as you know, open source R has limitations on memory usage. So when we are talking about big data, the application in R might just crash. But SAS has more capabilities. It is able to use more efficiently the resources of a computer, not just the random access memory. And in the intermediary data sets that I got, some of them are useful as input for other modules, like the chain ladder package in R language, or for example, this package chain ladder expects us to give the data already in the form of lost triangles, but we don't have by default that grouping. We just have the data from the underwriter or the adjuster, and it's not very straightforward to group millions of data into a triangle that chain ladder expects. So overall, I was surprised by these features of SAS. It wasn't huge implementation. It didn't involve many lines of code. It didn't involve the usage of dozens of procedures. So SAS, in my opinion, has been a good option for implementing the reserve system, be it for insurance or the other industries that require or use the concepts and methods of reserves. So thank you for your patience, and I don't know if you have any questions.
Thank you, Ignacio. I'm going to open up the phone line.
Enter *1 to start the recording, or *2 to return.